Hello, I'm Mr. Yao. When I was a primary school and middle school student, I used to attend lots of mathematical competitions, including the International Mathematical Olympiad. And that's probably the reason that why I keep my passion in math Olympiad problems. I have a good friend, Professor Yu, the founder of Morningstar Institute. We were classmates when we were having PhD study in UC Berkeley. This summer, Professor Yu and his colleagues designed a problem set which is about AMC8 level. He invited me to give the solution of these problems. Today we have another speaker who is Ben.
Hi, I'm Ben. I'm a grade 7 student. I've also been doing math since primary. Last year I got lucky. I got distinction honor roll on the AMC8. I'm currently also an AIME qualifier. I hope to be able to improve in math in the future and maybe become as good as Dr. Yao.
All right, so now let's start. Problem 1. So that problem says that, let's read the problem together. So we have 1,000 people. So each person owned a cat, a dog, or both. So we know what? We know that there will be 3 cases. So 1/3 of the 630 people who owned a cat also owned a dog. And then they ask how many people surveyed owned a dog. So this question, I think when I first see this kind of type of structure, which is, it could be either one or the other condition or both. So what shall we think about, or what is the next mathematical structure? Ben, do you know the name?
A Venn diagram.
Yes, it's Venn diagram. So what does mean a Venn diagram is? So Ben, maybe you draw the Venn diagram of this situation. You can use it. Yeah, so I think Ben has a good habit. When you're doing math problems at home, and definitely you have lots of different colored pens or pencils. So you can use the different colors to illustrate the different situations, and then that can help you solve this, can find the correct mathematical structure. Okay, so now let me quickly finish this question. So 630 people owned a dog, which is what? Which means the green circle. So the green circle is, so I just write down 630 on the green circle to show that this 630 is the whole thing. Actually, it's the union of the 2 parts. And then they say 1/3 of these people also owned a cat, which is the center part. So the center part would be 1/3. So you can calculate that directly. It would be 210. So this is 210. What the question is asking, how many people surveyed own the dog? Also owned a dog. Sorry. I think I read it wrong. That 630 should be the other way around. So this 630 owns a cat. So 630 should be here. And so here is 420. And then the question asking, how many of the people surveyed own a dog? So it would be just besides these 420 people, right? So what would be the answer? The answer is just 1,000 minus 420, and the result is 580, right? So you see, this is also a way that if you can denote all the conditions in a nice diagram, that really can help you figure out the mathematical structure. All right, that's problem 1. Now let's see problem 2. So it's a square root problem. I think this question is quite straightforward, but you just need kind of like to make sure that you're doing things in the right order. So square root of 81 is what? So square root of 81, that means what is whose square is 81? which is definitely
9.
9, right? And hopefully, of course, I think because the multiplication table definitely includes 1 times 1, 2 times 2, up to 9 times 9. I think it would be great that if you can memorize also a little bit more up to 20, like 11 square is 121, 12 square is 144. For example, what is 19 square?
361.
Yeah, so it's better that you remember all this, and then that can help you. And now if we have this, then we just continue our calculation. So it will be 81 times square root of 81 is 9, so it will be 9. Okay, so you can get that. But here I think there's a little trick, which is you do not really multiply that out. Of course, if you multiply that out, you would get a nice number, which is 729. And we will see it's actually also 729 is perfect square. But the better way is that you just split the square root. Then it becomes square root of 81 times square root of 9. Then everything becomes trivial, right? It's 9 times 3. So that is 27. Yes, 27 square is 729. So problem 2 finishes. And next, we move on to problem 3. So the market price of a book was 30% less than the suggested retail price, right? 30% less. So after you read this condition, you should know that what is the price? The price actually should be 1 minus 30%. That would be 70%, right? After the discount. Now let's read the second sentence. Alice purchased the book for half of the market price at the 50th anniversary sale. So which means Alice purchased the book at the half of this price. So half means what? Means divided by 2. Okay, 70% divided by 2. So that would be 35%. So of course this is a quite straightforward problem. And C is the correct answer. Now let's see problem 4. A square of integer side length can be completely covered by a circle of diameter 10. So when you see these conditions, Ben, do you have any kind of like typical picture in your mind up here?
Something like this. Oh, whoops.
So here is a circle. Sorry that we don't have an advanced tool to draw very elegant circles. Perfect, right? I think probably you already encountered some question which is kind of like related to that. So a square which is completely inside a circle, and actually that is called inscribed square. And then given that it's a square, so we have what? We have lots of symmetry. For example, that if we draw this tool, that should cut this circle into half. So this would be a diameter, so the middle point should be the center of the circle, should be also the center of the square. So we have such things like that. And then, the typical structure when a square has been cut into 4 right triangles, and these right triangles are not only right triangles, but because all the legs are the same, so we have lots of things called isosceles right triangles, right? So for isosceles right triangles, what I hope you could remember would be this, which is in the isosceles right triangle, what would be the side length of the 3 sides? It would be 1, 1, and the hypotenuse is?
The square root of 2.
Yes, and that is by Pythagoras theorem. Okay. And if you have this kind of typical structure, then I think the calculation would be quite easy, because if we have the diameter is 10, so the radius is 5, so it's 5, 5, and of course, the side length of this kind of like the inscribed square would be 5 times square root of 2. So 5 times square root of 2, and of course, if you know that what is the approximate value of square root of 2, which is 1.4142. You can get this is roughly like 7.05, which is slightly bigger than 7. So we could know that we can put, if the square has integer length, we can still do 7 by 7 in that circle. But if you see that, what happens if I don't know that approximate value of square root of 2? But you can still do it. So what is the way? So in the previous, I think, 2 problems where we deal with square root of 81, what we want to do is we break down the square root. So we get things out of the square root. And now what we can do is we can get things inside the square root. If we put the things inside the square root, what we have? We would have 5 squared times 2, which would be square root of 50. Of course, square root of 50 would be greater than square root of 49, and that is 7. So that is another way that we can get the approximate value. And of course, I think if you want to think about further, what you could think is you can think another situation where the circle is inscribed in the other big square. And you still use this kind of basic relationship for isosceles right triangle. I hope you can figure out the side length of this yellow big square versus the side length of this green smaller square. Alright, so that's problem 4. Now let's see problem 5. A soccer team played 3 games. Each game is either a win, lose, or tie. Okay, so that's good. In total, the team scored more goals than were scored against them. Which of the following combinations of outcome is not possible for this team? So from the number of goals, what we know is it looks like they have, this team is relatively strong, right? So when we look at the condition, what we should do, we should definitely look at the condition that the result that describe this team to be very weak, and which would be which one?
This one, C.
Yes. Then Ben, can we prove that C is actually the correct answer? Because we check the number of wins, there will be 1 win, there will be 2 wins, so only C has 0 win. So, but can we prove that this case is impossible?
Yes. We just need to count the number of goals that they scored in comparison to the number of goals that the opponent's team scored in total.
And yes, so from the ties, it means how many goals they win, and it is exactly the same as how many goals that the other teams win. So that will be kind of like the equal relationship here, right? But here they didn't lose the game. Only one, besides the tie game, they lose a game. So in that game, the number of goals that this team scored must be less than the goals they lose. So this condition cannot be met. So that's why the problem 5 is an easy one. So, but what you get is you get some kind of like a general idea. The general idea is this team is good or bad. Good. So you look for bad cases. So that applies also similar in lots of math problems. So if you want to solve some number, you first have a guess on how large could be this number. And then that may help you to find out the solutions. That's problem 5. And now let's see problem 6. A team of 8 construction workers finished 2/3 of a project in 30 days. And then 4 more workers joined the team to finish the remaining part. What is the total numbers of days this team has spent on the project? So Ben, what's your idea?
To look at the number of days left, which is 15, and then look at how much.
Why 15?
Because 2/3 of the project was finished in 30 days, so 1/3 would be half of that, so it would be 15 days.
Yes, so which means because there will be more people joining the project, so that in whatever the result has to be, so for the remaining part, it has to be finished less than 15 days. So the answer has to be in total less than 45. But unfortunately, all the answers are less than 45. Okay. And so then what's next?
We can look at how much faster their construction speed is with 4 more workers.
Yes. So you can look how much faster. How much faster is like kind of from 8 to 12 is, you can see, is 50% faster.
Yeah.
Oh, you can see the ratio is 2 to 3. Then it looks like 33% or something. I think definitely this way works. But we can have a quicker or more direct method. So what is this? What is this project, right? And how about we think this project is just like every construction worker needs to eat 1 candy per day, and the project is just to finish all the candies in a bag. Then let's see how many candies. So 8 construction workers, right? They have already worked out 30 days. So that means we could have 8 times 30. So what I'm talking about candies, of course, is a joke. But what I write here means you just think the workload that 1 worker work 1 day. So then that means for 2/3 of all the project, what is the workload? The workload is 240, right? So 240 is 2/3 of the total workload. And then that means the remaining 1/3 of the workload, if expressed in terms of this unit, it will be what? It will be 240 divided by 2, which is just 120, right? And for this 120, then how many workers are there? 8 plus 4. So there are 12 workers, so they are going to eat 12 candies a day. So how many days would it need? Then that's directly 120 divided by 12, and you get 10. And 30 plus 10, of course, D is the correct answer. So actually, in this question, what I want to show you is, so you have to set up the proper unit. Actually, this 240 is like we use a small unit, and the unit is a workload of 1 person to work in 1 day. And then everything, you have, besides the original given condition, 2/3 is a fraction, all the other numbers are integers. So you see the calculation is quite straightforward and simple. So that is why that you can solve the AMC8 questions, because each question you only have 96 seconds to solve the AMC8 problem. And so you need to find all the possible methods that can make you do the calculation and finish the question quicker, especially for easy problems. Now problem 7, a honeycomb. And the honeycomb has 4 layers. So what would be the first layer? The first layer is simple, so that would be the first layer. And what would be the second layer? That's simple as well, right? Okay, and then in that second layer, how many hexagons we have? We have 6, right? So when we want to form a summation, it will be 1 plus 6, right? So how to deal with the third layer, Ben?
We can look at the number of sides of each of these hexagons. Like, for example, there are 2 sides here, so there will be another 1 hexagon here.
Yes. And so we can count sides. If we count sides, this is kind of like we have a concave, right? Then we would have 6 concave ones. So maybe, I think also another 6 concave, yes. So maybe sometimes if we don't figure out the pattern yet, what we can do is we can just continue to draw and build up some knowledge. Okay, so now we know that we have 3, and these we have 6 hexagons, and all these hexagons has to be in the third kind of layer, right? And now the question is, there should be other hexagons in the third layer. Where are they?
They are in between these hexagons.
Yes, they are in between these hexagons. So if we just extend, then it would be that, right? Of course, sorry, it is not very up to scale, but still we get some sense. Right. All right, and now what to do next? Then that means, okay, so we finish this, and we know that how many are there, because you can count one by one, or you can, from our process, we know this third layer actually is 6 times 2, right? Okay, now the hard part is, what is the next layer? The next layer is 6, you can guess, right? The next layer, maybe 6 times 3, or maybe 6 times 4. Which case it is?
I'd guess 6 times 3.
And why is that?
Because for each hexagon, there seems to be one extra one on each part here, compared to before.
Yes, I think definitely your idea is correct. So what my observation is that, my observation is I look at, this is the center, right? So I look at this center together with this center. I just consider kind of like one direction and see how they extend, right? Then in this one direction, then you see that would be 2 2s, and then 3 3s, and then you think what happens. Then we can draw. I think we can draw things like that. That would be 4. That would be 4. That would be 4. That would be 4. And this is actually kind of like on one side, one, of course, because kind of one corner. And this one corner is actually about 1/6 of the whole thing. So the other way to see it, and also that's a typical trick in the mathematics. Actually, it has a deep meaning, which is related to duality. Is you consider the center of all these hexagons. What do you have? You see, these actually 3 points are in a line, and these 3 points are in a line. These 3 points are in a line. You get a hexagon. And for the 2, of course, you also get hexagon because there's only 6. So you see, it's kind of like the center of each layer, the hexagons in each layer would form a hexagon larger and larger, and it's just one larger. So that's why we can see, and also here is the situation, right? So you see here, this is one side, which has 4 centers lying in a line. So that's why it's true that in the next step, it's just 6 times 3. Okay, so now the result is clear. So 6 times 1 plus 2 plus 3, 6 times 6 plus 1. So the correct answer is 37, which is D, right? 37 is the correct answer. So you'll see that in order to find some pattern in some geometry, in plane or even harder geometry problems, so my suggestion is you just do it. Just draw the picture more clearer, and then it would help you to find the pattern. Problem 8.
Each of the following 15 cards has a letter on one side and a positive integer on the other side. What is the minimum number of cards that need to be turned over to check if the following statement is true? Note: if a card has a lowercase letter on one side, then it has an odd integer on the other side.
So it has the lower letters on one side, then it has an odd integer on the other side. So we need to verify that this is true. I have to figure out how to do it, but I think among these 15 cards that has been shown, we can definitely show that because it's related to lowercase and uppercase, and related to odd integer and even integer. So one thing we can definitely do is we can do kind of like a quick count. So how many cards that currently showing are lower cases, and how many are kind of like upper cases, and how many odd, and how many even, and we go from there. So among these 15, we can see there's only one card which is lowercase. There will be even number, will be 1, 2, 3, 4, 5, 6, 7, 8. right? So 8 number with all with 8 cards with all numbers showing an even number. We only have these 2, right? And uppercase we have 1, 2, 3, 4, right? Should add up to 15? Yes. So it's add up to 15. What's next?
We need to look at which ones we need to count.
Yes. So among these 4 cases, we just see which cases we need to count, and then we can go from there. Minimum numbers that needs to be calculated, that needs to be verified.
So we can start with a sort of logic chain. So
Yes.
we know that we have to count this lowercase because we have to verify that it has an odd integer on the other side.
Yes, so this case we must need to count. So this one we have to count. Okay.
And then we can start thinking. It does not say that if a card has an odd integer on one side, it has to have an even integer on. It has to have an uppercase letter on the other side. So, for example, I could have, say...
So the question is actually, we can just think of an example. The question is whether we need to turn this card or not. Do we need to turn over this card in order to verify this claim?
Let's see. So, let's say for 17, on the other side, we have an uppercase letter. Let's say it's A.
Yes.
So, does it satisfy the condition?
Does this affect the condition? No, right?
Yeah.
Because it is not lowercase anyway. And another situation would be if we have 17 and they do have on the back end they do have a lowercase, but does that affect the condition? Of course, it fits the condition, but it doesn't matter. So what by this kind of analysis it means no matter what's on the back end of this odd integer, it cannot. There's no way that you can make it this wrong. This is always true. So which means what? Which means we don't need to worry about these 8 cards. We don't need to flip it. Whether it's when you flip it, whether you get an uppercase letter or you get a lowercase letter, you would not need. They will have no harm for this claim, right? Then when you can think about the uppercase.
For the uppercase letter, it does not matter whether it has an odd integer or an even integer on the other side, since the problem asks for a lowercase letter.
Yeah, so this does not need. Okay, so definitely for the even integer, we need that. One reason is because the smallest choice is 3. The other reason is we can think, we need to flip this 60 because if it is a small letter A on the back end, then this claim could be wrong, right? But it's a capital letter, then it's fine. So the final answer would be 3, which is just 1 plus 2. Yeah, so this problem is a little bit tricky. But the tricky part, and this is also the important structure in the logic, we need to see which is a condition and which is a claim. And so the order doesn't matter. Now let's look at problem 9.
ABCD is a square of side length 4. M and N are midpoints of AD and BC respectively. 2 particles P and Q start together from M and move along sides of ABCD. P moves counterclockwise with the speed of 1 meter per second, and Q moves clockwise with the speed 2 meters per second. What is the area of NPQ after 2021 seconds?
Yes. So this, I think one thing in this question we can see is P and Q have no relationship kind of at all. So they are independent. So you only need to figure out where is P and where is Q. You kind of like do this step, to do a similar kind of calculation twice, and then you can locate where is P and where is Q. So P moves counterclockwise with speed 1 meter per second. So 1 meter per second, that means 21 meters. While the perimeter of AB is 16, right? So I think we need to do, for P, what we need to do is we need to use 21 divided by 16 and see what happens. So 16 and 42 232. There will be 101, so we get 6, right? So 96. So the remainder is 5. So it means after they move, this P moves starting from M, right? So they move like 126 circles, then plus additional 5 meters. So where it will be? So clockwise, right? Counterclockwise. So 2 and 3. Am I right?
Yeah.
Then we can repeat a similar process for Q.
It moves at 2 meters per second, so we have to be dividing dividing using 4042. But instead of doing 4042 divided by 16, we can just do 2021 divided by 8.
Yes, that's right. But actually, there's an even quicker method. Ben. So what we should do is we should just double 5. Because you double the 2021 divided by 16, the remainder would be what you get 252. Actually, you get 253. You have 5. So the remaining. So you double this number. Then you keep the divider the same. Then that means you double the remainder. The remainder double would be 10. 10. That's it, right? Yeah. Because that's 10. So which means we have to go clockwise for 10 meters, right? So this would be kind of 2, 4, that's 8, right? So the other is 10, right? So am I right? Is that just in the speed, right? Okay. So if that's in the speed, then we have a nice, this question is so simple, right? Because it's NPQ. This is, we see that this is 1, this is 2. So what it would be area? The area of triangle NPQ is just a half times 1 times 2, which is 1. Okay, cool. B is the correct answer. So that's why you see that you have to find the tricks that you can save your calculation time. Okay. Problem 10.
A 3-digit number ABC is divisible by 5, but not by 6 or 7. The number CBA is divisible by 6, but not by 5 or 7. The number CAB is divisible by 7, but not by 5 or 6. What is the remainder of ABC when divided by 11?
First, we see that this is a 3-digit number. It's kind of like cyclic. We have ABC, we have CBA, we have also CAB. It's not exactly cyclic. But what we can claim is, given that C appears as the leading digits, so here C cannot be 0. And given this number is divisible by 5, so C must be 5. So that's the easy thing. So now when I write the condition, I will just ignore the 5, but only focus on A, B, and other situations. So A, B, 5. And it's not divisible by 6 or 7. So I will use, we will normally use a bar to denote by the divisibility. So it's not divisible by 6. And AB5 is also not divisible by 7. Okay, so next, what CBA is divisible by 6, but not by 5. And so CBA is divisible by 6. Now let's look at this condition. What does it mean? Because CBA is just C is already, we know C is already 5. So this will be 5, right? And the 6 is what? 6 is not a prime number. 6 is 2 times 3. So that two conditions remind me that we need to think whether these two numbers are divisible, are multiples of 3 or not. What do you think, Ben?
I think it's a multiple of 3.
Yes, because these, so we do a little bit abstract argument. So this is divisible by 6. So it's divisible by 3, right? And then that means in order to test whether a number is divisible by 3 or not, it means the sum of the digits has to be divisible by 3. Okay, So the sum of digits is divisible by 3, then it means what? It means this sum of digits is also a plus b plus 5, because it's just like the rearrangement of this 3 digits. So this is also must be divisible by 3. So AB5 is divisible by 3, but not divisible by 6. Yes, of course it's not divisible by 6 because it's odd number, right? So actually we know what all these kind of arguments don't really help us too much yet, but at least we know this condition is useless already, right? Okay, so now we need to continue. The next condition, CAB is divisible by 7, but not by 5 and 6. Okay, CAB is still 5, AB is divisible by 7, but not by 5 and not by 6. So that means B is not 5, right? So it's not by 5, not by 5 means A and B are both not 5. Okay. Okay, so this would be the situation. Now what to do next? But I think anyway the idea is we find ABC, right? And then we divide it by 11. That's always the last part. So then what is the most efficient way that we can find A and B? We get C. But we haven't be able to find out A and B. So what shall we do? Any idea, Ben?
Well, we can note that since 5AB must also be divisible by 3, 5AB is also divisible by 21.
Yes, so that's a great idea. Because 5AB is divisible by 3 and as the sum of the digits as divisible by 3. So these two conditions combined, we know that 5AB is divisible by 21. Then what's next? Here it contains a very important trick, and sometimes people forget, because when we're talking about divisibility in mathematical Olympiad, what we do? Oh, we have divisibility rules. We have divisibility rules for 3, for 5, or some even remember the complicated divisible rule for 7. But actually, the one useful tool is actually is you just use the definition of divisibility. So what is the definition of divisibility? It just means when you divide, if some number is divisible by 12, right? So you really get the division. You really divide this number. It actually has remainder 0. So what I do? Is I directly go to that. I directly go to 500. I divide it by 21, and I want to see which number, which 3-digit number starting with 5 would be a multiple of 21, right? So we get 4, they get 22, 42, there will be 80, there will be 3, so that will be 63, that will be 7, right? So, okay, so then in order to make it a multiple of 21, we add up 4, right? 17 plus 4 is a multiple of 21. Okay, so we know that 504 is a multiple of 21, right? However, we said that A and B, because A and B are actually, we check whether this number is good or not. But we notice that because when we flip, it's not a multiple of 5, means A and B not only is not 5, it's also not 0, right? So this is not a good case. So we have to continue. Then what to continue? We just add up 21. So we have 5, 25. This is not good as well. This is not good because of 0. This is not good because of 5. Now let's continue. 5, 21 will be 46. Is this good? No, right? Because this has to be, so actually we should see that this has to be, because it's not divisible by 6, means this number actually has to be odd, right? So this is definitely not good. And that has to be next. And which would be 567, right? And that's it, I think. Because next one would be an even number again. So the next would be beyond 500. So the answer must be 567. So original ABC is what? The original ABC is 675, right? So ABC is 675. When you divide it by 11, actually you can get, this is 11 times 61 plus 4. So the remainder is 4, right? Yes, so this is a nice question. And also you think this is interesting. In the end, the 3 digits are just 5, 6, 7, and all the divisibilities are related to 5, 6, 7. Okay, so this question really contains some tricks. But here, this is the trick that I see. I normally see this is called brutal force. Or a more elegant word would be called what? Enumeration, which is that you just list out all the possible cases. If there are not that many, right? If there are 10,000 cases, probably we cannot handle humanly. But if there are only like 4 or 5 cases like this situation, you just list out, and then you will get the answer. Problem 11.
The area of the triangle bounded by lines y equals x, y equals 2x, and x plus y equals k on the coordinate plane is 12. What is the number k?
Okay, so for these, it seems that we have to draw a graph, at least a sketch of the graph to start with. What I'm going to draw is I'm only going to focus on the fourth quadrant. And because it will be y equals x, and then y equals 2x, and then x plus y equals k, it will be something like that, right? X plus equals k. So then that means here is k, here is k. And this is y equals x, this is y equals 2x. So how shall we solve it? I think the idea is what we can do is we can try to see, definitely this looks, the triangle looks like to be here, right? So this triangle is what? This triangle is a big part of this big triangle. And that big triangle is something that we have seen before, which is the isosceles right triangle, right? And for this isosceles right triangle, and the side length will be k, and square root of 2k. So what we can try to find out is we can try to find out what is the fraction of this triangle versus the big one, right? So how to find that one? What's your idea, Ben?
You can possibly focus on this point.
Yeah, so this point, and so actually you can see this point, this is 45 degrees, x plus y equals, and this is x minus y. So this is, if we extend this a little bit, so if we extend that, actually we will get, it's a square. So this must be the midpoint. So in other words, it means this is a, midpoint of this whole line segment. If we want to write down the coordinates, actually you can calculate the coordinates will be k over 2 and k over 2. So that would be this point. Then how about that point? That point, and we know it's y equals 2x, right? Y equals 2x, and x plus y equals k. So we can try to use the ratio relationship to find this kind of like system of equation. So we can quickly solve it and to get what is x and what is y. So x is k over 3, and y would be 2k over 3, right? So after you get this, then what is the geometric meaning? The geometric meaning would be, you see, the x here is k over 3. So which means this should be 1/3. If you use a similar triangle, you know this will be 1/3 of this slanted line. And this is the middle point. So what I mean would be this area of the shaded square, the shaded triangle, versus the area of this big isosceles right triangle. What the ratio? The ratio would be like how long of this line segment versus the total line segment, which is just half minus a third. So half minus a third. And the result is 1/6. And then what is the area of this? The area of this, we know that it is, now we can form a quick equation. So this will be 12 is the area of the shaded triangle, and this, the ratio is half k squared, and that equals 1/6. So what do we get? So actually what we will get, if you multiply this, you get 72. Half k squared is 72. So k squared is
144.
Yeah, 72 times 2 is 144, or in other words, is 12 squared. So k is 12. That is the answer. Problem 11 finished. Now problem 12.
How many positive integers less than 50 have an odd number of positive integer divisors?
So that question, I think it's easy if you know the result. And the fact is, for any number that has an odd number of positive integers, that number is?
A square.
Yeah, it's a perfect square. So it would be just like, so less than 50 would be 1 square, 2 square, 3 square, 5 square, 6, less than 50, 6 square, 7 square. So there will be, if you got 7 square, it's already 49, right? So the answer would be 7. But let's quickly review why for perfect square, then the number of integer divisors would be odd. So we just start with, maybe we just do this 36. So 36, suppose we don't know whether it's a perfect square or not, we just do it one by one. So 1 is a factor because 1 times 36 is 36. So this is a pair of the factor. And then next, what it is, 2 times 18. And then you try next. You try 3 times 12. And then you try next. But then next, what you have would be you get 6 times 6. So here, this is repeated, right? So that's why when you count how many divisors are there, you get 3 pairs plus 1. So that is why it's an odd number. However, if you have the normal case, which is not perfect square, for example, like 24, what will be the situation? It will be 1 times 24, it is 2 times 12, it's 3 times 8, it's 4 times 6, right? So you get 4 pairs. You always get many pairs. But in this case, when you have a perfect square, so for one particular pair, the 2 factors in them are the same, right? So that's why it's an odd number. That's problem 12. Now problem 13.
How many different 5-letter words can be formed by using all 3 letters A, B, C, and the middle letter has to be B? For example, A, B, B, C, C, and A, C, B, C, A are 2 such words.
Okay, so all the letters have to be used. And, okay, so the middle letter is B. So when we fix whatever, it is already fixed. So there are 5-letter words, so B is in the middle, and there will be 2 letters at the beginning, and the 2 letters after it, right? And what we want to know is, they say that all the letters has to be appeared, right? So what would be the situation?
So, for each of these spaces, we have 3 choices.
Yes,
A, B, or
nice.
C.
Each we have 3 choices. So then, without any restriction, then by the multiplication principle, so there will be 81 ways. But of course, we have restriction, and the key restrictions is, and can be formed using all 3 letters. The key condition is we have to use all 3 letters. There has to be A, there has to be B, there has to be C. And then so what?
We can eliminate the conditions, eliminate the possibilities that don't have all 3 letters.
Yes. So the reason why I do elimination, or in other word, here it is a trick, which is that you count here because it's a counting problem. Or in other cases, you do calculation. Your calculate is complementary, and why that is because you see, for the cases that we in here, so there could be like 1A, there could be 2A, there could be 3, at most 3A's. So there will be so many situations. But for the complementary situation, it will be fairly easy. There are not that many cases. What are the cases? So there will be 3 cases, I think. The first case would be it only contains letter A and B. The second condition would be the only contains letter C and B, so that it only contains 2. And what would be the third case? Because there's always B. The third case would be that only contains one type of the letter, which is B, right? And so now the situation, I think, becomes relatively easy, right? Because of what? So how many cases that it contains both A and B?
So for each of these lines, instead of having 3 choices, we only have 2. So 2
So
times.
yes, so it will be 2 times 2 because each position can be only A or B. So that will be 2 times 2 times 2 times 2, which is 16, right?
And then for C and B, we can do the same.
So, yes, for C and B, we can do the same, which is 2 times 2 times 2 times 2, which is 16 as well. Then, how about case 3?
There is only 1 choice now, so this becomes 1.
Okay, so then if that is the case, what would be the result? Let's list out the result. The result would be 81 minus 16 minus 16 minus 1, right? And then the result is 81 minus 33, and we get 48. That's strange. Because
we repeated a case. So in here, we repeated this case before.
Yes. So after, we get a 48, which is not in any choices, then we know there must be something wrong. And that something means we have to do, what are the repeated cases? Because the repeated case would be O, so only B appears, right? So actually it means we have to avoid this case, because this case contains no A. There has to be at least 1 A, right? So this has to be changed into 15. And this has to be changed into 15. And then what would be our answer? So our answer would be 81 minus 15 minus 15 minus 1. Right? And the result is 50. So now we need to check whether is that we did something wrong or whether we missed something. I think the ideal case would be we try to find another method to see whether we can solve this, right? Then what would be the other method? The other method, we just think, okay, they have using all the three letters A, B, C. So there should be 1A, 1B, 1C. And then we just see what are all the possible cases, right? It could be, we just listed out all without any order. So I have limited space. Maybe I write here. So 1A, so it could be, the number of three letters could be either 1, 1, 3 or 1 to 2, right? So we could have 1 to 2, it would be A, B, B, C, C. And it could be B, A, C, C. It could be C, A, B, B. That means without the order, right? And there's also like cases with 1, 1, 3. So it could be A, B, C, C, C. So it could be A, C, B, B, B. Or it could be B, C, A, A. Now, what we do is we need to consider for all these 6 cases, we count how many possible letters in each scenario and we add up, right? So the easy one would be you do this. This is only contains 1B, so B is already used up. So you need to put 1A and 4C. So how many ways are there? There will be 4 ways, right? So you select one position for A, then that will be it. Then how about this? This would be B, and then there are 4 positions. You select 2 positions for A. So that would be 4 choose 2. So you have 6 ways. Okay, so that's already 10 ways. Then can we do the rest? And so here we cross out 1B, so there's 1A, B, C, C. So we select 1 position for A and 1 position for B. So that means it has 12, right? And so here it is similar, right? Because it's CA, AB. So there's another 12. How about here? It's the same, right? So there's another 12. How about here? This would be CAAA, 4, right? Okay, so what do we have? 36 plus 14, right? Okay, 15. So we know that this time 50 is the correct answer. So you should not choose any answer out of A, B, C, D, E. Okay, that is problem 13. Now, let's move on to problem 14.
A student has 2 open-topped rectangular containers. The walls of the 2 containers are thin enough so that their width can be ignored. The larger container is a cube of side length of 10 and is full of water. The smaller container is 5 times 5 times 9 and is empty. The student slowly lowers the smaller container into the larger container, as shown in the following picture. As the smaller container is lowered, the water first overflows out of the larger container and then eventually pours into the smaller container. When the smaller container is resting on the bottom of the larger container, what is the depth of the water in the smaller container?
Yeah, for this question, I think it's kind of like a physics problem. And what we need to do is, so hopefully when Ben is reading the question, you already have some idea about how the process. So I'm going to quickly to read to draw one of the middle steps. So one of the middle steps would be something like that. Where, because this is the height is 9, the total height is 10, so it would be something like, so the top face is kind of like just on the top of the big container, but while for the bottom, they haven't touched the bottom of the big container yet. So then what would be the difference? The difference would be only 1, right? And then only under this situation, so there will be already some water out. The amount of water out is exactly the volume of that smaller container. So next, after you push down further, you will see that all the water flow in, right? And so in the end, so what is the next situation? The next situation would be this big container would be lies inside exactly lies in the touch the bottom face. So then that means there will be the gap here would be 1. So which means what to think about it would be you just think this bottom 1 volume of water has to be disappear. So it's kind of like this, you have to cut out this, then all the situation would be still like the smaller container was surrounded by water, and all this water have to be put inside. And then what would be the height? So here height is 1, but if you calculate the area of the 2 containers, one is 5 by 5, the other is 10 by 10. So the ratio is 1 to 2 to 1 to 2, so the ratio is 1 to 4. So this is only a quarter of the area is only a quarter of the big one. So the height, when it goes inside, it has to be multiplied by 4. So that's why the height would be 4. So this would be more, there's not really any calculation needed. It's more like you do an observation. Then that should be fine. All right, problem 15.
6 numbers 2, 3, 4, 6, 8, and 12 are put in the following circles. The products of 3 circles in triangles A, B, and C are the same. What is the sum of digits of the largest possible value of that common product?
Okay, so we want the common product to be as bigger as possible. The product of 3 circles A, B, C, right? So the product of these 3 numbers, that's 3 numbers, and that's 3 numbers. So then what we'll see the difference. The difference is altogether, so each circle has 3 numbers. So 3 circles, we actually have 9 factors. But why we only have 6 numbers? So what's the difference here, Ben?
9 factors and 6 numbers. The difference here is that these 3 circles will have their numbers considered twice.
Yeah, this number will be computed twice. Now we want to do the product on each triangle to be big. So that means we want the product of all the numbers to be as big as possible. In other words, it means we should aim to put the 3 big numbers just on these 3 numbers so that they could multiply the second time, right? So then we can just try like 6, 8, and 12, right? And then in order to make the sum kind of like, so the product will be the same. So one we already have 6 times 8. The other is we already have 6 times 12. And then the other one is 8 times 12. And so the relationship would be 48, 72, and 96. There's a common factor, 24. So the ratio would be 2, 2, 3, 2, 4, right? And so what shall we do? But then all the other numbers left are 2, 3, 4. So we cannot really form the product. The only thing is, so that means probably we have to make it slightly smaller, right?
Maybe we can try 4.
Yes, if we try 4, then maybe we can quickly calculate the other thing. Is 4 times 8 is 32, and then 4 times 12 is 48, and 8 times 12 is 96. So here the common ratio would be 16, right? So it would be 2 times 3 times 6, right? And what the thing left? What the thing left would be 2, 3, 6, right? Can we do that? Because the thing left would be 2, 3, 6. It's again 2, 3, 6.
So it still fails.
So it still does not work. So 4, 8. So which means we change to, then that means maybe we have to drop out 8 and try 4, 6, 12. Wouldn't that be the case? Yeah, so it's 4, 6, 12. Now, let's just write it here. So it will be 4 times 6, which is 24, and then 4 times 12, which is 48, and 6 times 12, which is 72. And the ratio would be 1, 2, 2, 2, 3, right? And then the thing left would be
2, 3, and 8.
2, 3, and 8. Can we do that? No, because 8 is too big, right? So let's see, what shall we do?
We can try 3, 8, and 12.
Yes, maybe we can try 3, 6, and 12. 2, 4, 8. So which means the biggest one must, so we must put 8 here because it's the smallest one. And next one is 4, is right? Yes, because these are two relationships. So this will be 18 times 8 is 144. And this is 144 as well. And this is 2. Okay. All right, we get that. And so what is the sum of digits of the largest possible value is 144. And the largest value would be 9.
I think maybe we can make sure that 3, we can also check that 3, 8, and 12.
Yes. So for this question, we
to be
do have
safe.
some, actually for this question, we do have some detour. But now I get some idea. So what is the idea? And that idea also related to, which is a very basic idea in number theory, and which is called factorization. And this is a part that we don't really do it, because here we are dealing with a product, right? So you could see that how many 3's we have. So here there's a 3, right? Here there's a 3. And here there is a 3. So there are only 3 3's. If you put 1 3 here, and so where to put the other 2 3's? Either you put all the numbers and multiply 3 in here or in there. You cannot put something here and something there, because then when you form the product, how many factors of 3 are there would be not be able to allocate evenly. Like say you put 2 numbers here with a multiple of 3, and then so here they have 2 3's, and then you need to have 1 3 here and you need to have 1 3 here. So that's why I think now we feel comfortable why we don't need to try more, because this is the case where all the multiple 3 are in the middle, right? Okay, so 15 finished. We are 75% finished. Now problem 16.
A strip of paper 1 centimeter wide is folded 4 times to make a regular octagon as shown. If the ends of the strip meet exactly when folded, how many centimeters long is the strip?
Okay, so we don't know the length, but we know that these kind of things are finally kind of folded up together. And what we know would be the width, right? So we know the width, so what we know. So we can see what we have. If we write down what we know, this is would be y, right? So here it would be y, and here would be square root of 2, and square root of 2, and so on, right? And the only thing that we don't know is what? The only thing we don't know is what would be the size of the middle square. That is a part that we don't know. Oh, okay, I know. Why? I overlooked the condition, and that condition is regular octagon. Okay, so Ben, maybe you can finish the rest of the calculation. Yeah, so the square inside it should be actually a square with side length square root of 2. Okay, so now we pretty much have all the kind of the length marked there. So what is the way to find the whole length parameter? So we'd better just focus on one side and we draw that one side, see how it is folded, right? So I will start with this line and just start with this line, see how it is folded, right? So can you imagine where it is here? It is there, right? And then here, and then here, and what? Then here? Am I right? I think it's right. And then here, right? And up to here. So maybe the last bit is not that correct. So it has to be, it's just continue this way, right? It should continue this way. And then continue this way, and then go up, right? So there should be 5 parts, right? 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5, 6, 7. It should be.
This isn't part of the side.
This is not part of the side. This should be not part of the side. Because after that, we should go down directly. Yeah. So we always need. So you see, at the beginning I made a mistake, but the thing is, I always double check the number of line segments. Then I can figure out the reason where I did it wrong, right? And then here, right? And then it is this one, right? And then that one, right? And so we know that what it would be the situation. And this is actually forms a rectangle. And this rectangle, inside it, it's a square root of 2. And so there will be, so how many square root of 2 there? There will be square root of 2. There is a square root of 2. There is a square root of 2. There is a square root of 2. How many 1? 1, 1, 1, 1. So 4 plus 4 square root of 2. So this is the correct answer. Problem 16 finished. Now let's move on to problem 17.
For I equals 1, 2, etc. until 20, AI is -1, 0, or 1. If A1 plus A2, etc. add to A20 is 1, and A1 plus 1 squared plus A2 plus 1 squared, etc. until A20 plus 1 squared is 37, how many of AI is equal to 1?
Okay, so I think for this question, Ben, what's your first idea after you see all these conditions?
That the number of negative ones and ones are the same.
Why?
Oh, sorry. No, there's one more one, the negative one.
Yeah, there's one more one, the negative one. So I think the thing is, when I first do it, we just think like how many negative 1 and 0 are there. We just see x negative 1s, y 0s, z 1s, and then we see what is the condition. So this first condition just tells us what? That just tells us z minus x is 1, right? Okay. So then how about the next condition? The next condition, when you add up 1, then it will become 0, 1, 2, right? So 0 does not count. So y, so that means it's y plus 4z is 37, right? And don't forget about what is the relation to how many numbers are there? There are 20 numbers. So x plus y plus z is 20. Wow, that's nice. It's just a linear system with 4 variables, right? It shouldn't be that difficult to solve. And so they ask how many ones are there. So maybe we can just try to start with trying z, right? So let's try, and then we can get some idea. So z is 6, then y is what? Y would be 15, right? And x would be 5. So add up is, of course, not 20. So z has to be bigger, so y would be much smaller, right? So if z is 7, then y is 10, and x is 6. So it's better, right? It sounds kind of like better. So I think we just go next. Probably that will be the case. So 8. So 4 times 8 is 32. So y is 5. And x is 7. Okay, perfect. 7, 8, 5. As common ones are there. 8. Okay. So that's why, in this question, there's a multiple choice question. Do not try to formulate nice equations to rigorously solve it. Just plug in the number, get some directions. Actually, when you first plug in z equals c, you will see because y is too big, probably you can directly jump to 8 and try. All right, now next we have a geometry problem.
2 circles, one of radius 1 and the other of radius 2, touch externally at P. A straight line through P cuts the area formed by these 2 circles in the ratio 1 to 2. In what ratio does this line cut the area of the smaller circle?
The area formed by these 2 circles by the ratio 1 to 2. And also we know that because we don't know, because all these kind of areas, now that's easy to calculate. The ratio is 1 to 2. And so we know that the relationship between the area of the 2 circles would be just 1 to 4. Okay, so what I have an idea is I try to use the symmetry. Right? So I use the symmetry, so I draw a line. So definitely this line that connects the 2 circles, so that line will cut the whole region into 2 equal parts, and it's symmetric with respect to that, right? The radius is 1 to 2. So what we know is what I'm going to, the area of this would be 1 to, the ratio of the area of the 2 circles will be 1 to 4, right? So what I do is I will do that. So I will label this 1. And then I will label this 4 because it's half the disks. So it's also 1 to 4. So then I label this x. I label this y. Then this would be 4 minus y, and that would be 1 minus x. Am I right?
Yes, I think we can also draw this, like an arc.
Yeah. So what you see is, you said maybe you can just draw a small circle inside the disk and see how the situation is going. And my idea so far is, given that we have this, then we can really form an equation that links x and y and see whether we get something. The formula expression would be, so 8, 4 plus 4 minus y plus x, right? That divided by 1 plus 1 minus x plus y, and the answer is 2, right? Okay. And then we change it into 8 minus y plus x equals what? Equals 4 minus 2x plus 2y, right? And then what we get, 3y minus 3x equals 4. We cannot really directly get what is x and what is y. All right, so what shall we do? I think maybe we can follow your idea, Ben. We just follow your idea and we see what happens, which is we draw a circle which is exactly the same as this circle, and so it will touch this center because it's 1 to 2, right? So then now let's see what happens. Actually, we do see some interesting things. What we see? Here it is x, right? You see? Here it is x, and then here it would be, because here it would be y minus x, right? And does that thing tell us something?
Actually, my idea was to draw a sort of larger circle. Sorry, my drawing is kind of bad.
Yeah, we can draw the large circle.
Use that these two areas are equal.
We can only get what is x, what is y minus x. So which means we can get the region of this part.
And then we can sort of use concentric circles to find that between this area and... So we can use the correlation between these two areas.
But these two areas, they are not really... Okay. So, yes, so this concentric area, so this one would be 1 minus x.
And then we can plug that into the calculations for these two, and then after
I think is this right? So then your question is related to I think we should have another condition, and that other condition, as Ben mentioned in the black lines, which is 4 minus y over 1 minus x. That is 4. Because this is kind of like, another way to see it would be, maybe I'll use this part. It's kind of like similar to that part.
Yeah, that's what
right.
I meant.
That is sort of, because all these angles are the same. It's kind of like you enlarge this twice, and so then there will be a 4 relationship. And then by that, we should be able to get the other equation. And then the other equation gives us 4 minus y equals 4 minus 4x. Okay. So these are the relationships. Okay, now we know the situation. So we should assume that these two have, so these two has 4 relationships. 4 times 1 minus. Okay.
We already
so yes, we already got it. So that means this gives us that y equals what? Y equals 4x. So the relationship between these to that is 1 to 4. So if y is 4x, so that would be 3 times 4x is 9x. So x is, y is 4x, so 9x is 4. So x would be 4 over 9. So what is the question is asking about? It's asking about how they cut the smaller area. Okay, great. So that would be 4 over 9. And then the other ratio would be 5 over 9 plus 1, right? And so that is 4 minus 5 plus 9, 5 plus 9 is 14, so which is 2 over 7. Okay, that's great. So finally solve this question. Okay, so now we still have 2 more questions to go, and hopefully it won't be as complicated as problem 18.
Dennis chooses 2 different unit squares at random from the array of 13 unit squares shown. What is the probability that the 2 squares share an edge?
Oh, that question should be easy because they already said there are 13 squares. So probability is nothing. Probability is just a fraction, right? So we draw a fraction, and how many possible choices are there? There will be 13 choose 2. And which is, we can calculate it 13 times 12 divided by 2. So it's actually 13 times 6, right?
78.
Yeah, so we don't really need to get 78 directly. Of course, here it's simple, because later on we could cancel out some terms, right? Now we just think the situation, when we select 2 terms, how many common edges are there? Then that's simple, right? We just count what could be the common edge. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? Okay, so 16 would be, I would write this as 8 times 2, right? And these cancel out, we get a 3. So the answer would be 8/39. Right, this is really a simple question. Finished. And now, finally, problem 20.
In A, B, C, E, J, G, and H are points and sides of ABC. EH is parallel to AC, JG is parallel to AB, and FI is parallel to BC. EH, JG, and FI intersect at K. If the areas of EFK, JKI, and KGH are 1, 4, and 9 respectively, what is the area of ABC? We could potentially use similar triangles, or I don't know if this works.
Yes, so you kind of like you cut it because all the parallel lines. So all these things would be, so there will be 3 triangles that giving with area giving together with 3 parallelogram, right? And so now here what you want to do, so you connect this, you get parallelogram. So but then what you guess is you guess whether these 2 lines are parallel or not, right? So that's what you guess, right?
Yes.
So you have a guess, which is FG, whether FG is parallel to H, right, from the picture itself. Okay, so I think, yes, this question definitely can be solved by using kind of like a similar triangle, but given we already have a very long lecture, so I'm going to tell you a slightly different method, which normally I'm pretty sure that you will not see in other books when we're solving this type of question. And by the way, this type of question, I think first would appear in AME, but now as year goes on, this could become the AMC8 level problems. So what is the trick? The trick is these 4 letters, GRID, or maybe GRIDS. So why we have 149? Of course, 149 reminds you about perfect squares. But how to express perfect square by triangles? So here's a way to express perfect square by triangles. 149. Okay, so what I do? So I do nothing. I just like to cut. I cut each line segment into 6 pieces, and I have to make sure that I cut it right. And 1, 2, 3, 4. We need to make the scale right. So to make sure to avoid any mistakes, so what we do is better that we get all the endpoints first. So here is 2. So here, because it's 3, so we are going to get 3 lines horizontally. So we get all the endpoints. So all the horizontal lines are good. And then here it will be 1. And then here it will be 3. And then here it will be 2. Then we get 1. And so that would be this direction. What about the other direction? The other direction would be that. Okay, now I finished. Then what will be the answer? So first, the answer is trivial because it is just what I drew is the extension of what I drew, right? So it is it's 1 plus 2 plus this is 1 square, this is 2 square, because this is 3 square. Each side has been cut into 3 times. Three smaller line segments, identical line segments. So here each side is cut into 6 smaller line segments. Of course, the answer would be just 6 squared, that is 36. And now we can also use this grade to check if Ben's conjecture is correct or not, right? Because if you connect this, right, and what you see. So here it is 1, 2, 3 line segment. Here is 1, 2, 3 line segment. So these two line segments are the same and parallel, yes. Then the other two line segments are parallel and identical as well. Okay, so I think that's all what we want to see. And thanks for your time. So you know that even you can argue that we are strong in mathematical Olympiad, but we still make mistakes, and we still cannot find the best methods at the beginning. So through this life experience, we just want to show you, it's interesting that you explore, and that is the beauty of mathematical Olympiad.